there is a transformer like this. And over here, there's a bulb with N2 of 1,000 turns. And then this bulb has a maximum power of 60 watts, and then it's a voltage of 120. Over here, there is a resistor and a battery, and this, or whatever, some EMF, and this voltage is 120 volts. Oh, actually, you know what, I should say, for this, depends upon the other thing, but this is 120 volts, which means this one, V2, has to be 1200 volts. This is 120 volts and an N1 of 100. Okay, that's what we know so far. So when I meant, so the first part of this problem says, what is the current over here, right? So this is, what is the current over here? Well, I'm given the power and I'm given the voltage. Well, if I want you to find I, and I give you P and I give you V, what equation do you use? Yeah, P equals IV, right? So for this, I just say P equals IV, so I is P over V. So that's 60 watts divided by 120 volts, and that gives me 0.5 amps. For the second part, they're asking what is the current on this side if you put a 60 ohm resistor there. So if you stick a 60 ohm resistor over there, what is the current on that side? Well, this is even easier, right? I just use Ohm's law. So R is V over I, because V is IR, so R is V over I, and V over there is 120 volts, and I is, wait, do we know that? Did I do the wrong one? We solve for 0.5 here. Crap. Okay. I'm solving for a given. That's awesome. That's just genius right there. We are given that there is a 60 ohm resistor, and the voltage is 120. So we're supposed to solve for the current. So I is V over R. Jeez. And then that's going to be 120 volts over 60 ohms, which gives us 2 amps. Part C becomes a little more interesting, because what we have to do here is kind of draw a line here and say, this is telling me the max current. If you run a current bigger than this, you'll blow this bulb out. Okay, what else? If what else is too big, will that bulb burn out? Have you ever seen a bulb blow out? Light bulb burn out?
Oh, burn out.
Yeah, you don't go like that. Okay, well, never mind then. So for part C, I'll do this in the yellow. Okay, so now this is where we're actually, part A and B have nothing to do with the transformer. But now we're dealing with the transformer. Remember, the two equations for transformers are P1 is P2, which gives you I1 V1 equals I2 V2, and EMF1 over EMF2 equals N1 over N2. So if we know that this side right here has a voltage of 120 volts, and we know the ratio of the turns, then we can solve for E2, because E2 is going to equal to EMF1 times N2 over N1. Does this make sense? Right? Now, when I plug that in, what I get is 120 volts times 1,000 over 100, which is going to be 1,200 volts. Now, I think anyone, even without a clear knowledge of electricity, can tell me what happens when you put a 1,200 volt current, or whatever, 1,200 volt electrical potential across a regular light bulb. Right? It's going to burn out. It doesn't explode. Bulbs don't really do that.
Can they?
Not really. Maybe if you pumped like 100,000 volts or something like that.
They'll actually explode.
It would be tough. In order to explode it, I think you would have to vaporize not just the filament, but the entire metal parts on the inside. Maybe that could happen. But that's movie stuff where all the light bulbs explode. That doesn't really happen. Okay, so now we know that this new thing's going to have 1,200 volts, but we need to know the current. So do you see the equation that I use? If I know the voltage in the new one, and I know the current and the voltage in the old one, what do I use to find the new current? There you go. Do you see this right here? Remember, so we used this first. Now we're going to use this because we can say, what is I2? I2 is going to equal, I'll just leave it here. I2 is going to equal I1 times V1 over V2. And what was I1? 2 amps. And then, so we have 2 amps here, and we have V1, which is 120 volts, over V2, which is 1,200 volts. So then that gives us 0.2 amps. So even though the amps, the current is very low, it's still going to blow out because the voltage is just too high. So remember, the voltage is too damn high, party. Kind of figured you'd be the only one who got that. There was this crazy looking guy who ran for like what, mayor of New York or something? Or governor of New York. Governor of New York. And James Douglas. Yeah. And he said, I'm a member of the rent is too damn high party. It's pretty funny.
Oh, did you hear about that bullet guy?
Okay, so that one blows up.
Sorry.
Now for part D, sorry, up. Yeah, the bulb's gonna burn out. For part D, the question is, well, what do you do to this resistor, this one, the 60 ohm? What resistance could we put in that would actually make this not blow up? So what do we do to this resistor over here to make this blow up? Just by using common sense and not having any knowledge of the numbers. What would you do to this resistor to try to keep this one from blowing up? Would you make it bigger or smaller?
Bigger.
Just logic says, okay, there's too much power going on, so I'm going to try to reduce the power and see what happens. In fact, if we take a look at this circuit, how much power is on this side of the circuit? Exactly, these two powers are going to be the same. How much is over here? If we have a current of 2 amps and we have a voltage of 120 volts, do you see that over here for this one right here, or for both of these, we have 240 watts. That's why the bulb burns out. So what do I have to do to the power on this side to get it to match this side? I'm going to have to, your first answer was, I think you're answering 2 questions at once. So let me take both of your answers. Her first one was divide it by. So do you see we have to reduce or divide the power by 4? Yes? Now, if you want to reduce the power by 4, what do you have to do to the resistor? Increase it by 4. So our guess is going to be, I think, I'm going to put a little guess here. I think it's going to be 240 ohms. That's my guess. But how do we do that? Well, this is how we do it. I'm going to do this in, I don't know, let's say green. We want this power. How do we measure that power over here? We said power is equal to current times voltage. Can we change the voltage? Oh, here, some people can't see this. Move this up. So can we change the voltage? Like if you put in a new resistor, does that change the voltage? No, it does not. Right? The voltage comes from a battery. We can't physically change the battery just by adding junk into the circuit. So we can't change that. But, so to change the power, what do we have to change? The current. And what we know here is V is IR, right? Right? So I is V over R. Wait a minute. Therefore, and we knew this already, right? R is equal to V squared over P. Is this recording? I hope so.
Yeah.
So what is our V for the left side? It's 120 volts squared over our power that we want. This is a power we want it to be, 60. That's going to give us 14,400, I think, over 60 watts. Knock that out, and you get 240 ohms. And our guess was correct.
Wait, where's the V squared come from? The voltage squared?
Remember how this equation, P equals IV, if you use V equals IR, you can get 3 different equations? I squared R, IV, and V squared over R.
Oh, it's just,
Yeah, it's just one of those. So basically, for part D, it's just, all we're saying is, I just want the power to be 60 watts. I can't change voltage, but I can change the resistance. So I increase the resistance so much that I get a 60 watt power, and that tells me that I need 240 ohms. And that, ladies and gentlemen, is it. Questions? Alrighty.